So this is a problem topic on isomers, and there are two problem topics, and this is the first one. And they ask you about the chiral isomers, which means chiral means also we call optical isomer. Isomers of chromium in the center, 2 chlorines, and the 2 En. Once again, the En is essentially diamine. So you can think about the bidentate molecule looks like that with NH2, NH2, and those are the ones that lone pairs love to make a coordination. So it's complexes. So how you count this? The number of ligands here is you got 2 ligands, and then you got 2 times 2 because they are bidentate. So this is a 6 ligands, right? 6 ligands. You're thinking about octahedral structures. Octahedral structures, as I shown up, this is actually what I find out from your your reference, the class lecture slide, and I would like for you to envision yourself something looks like this. So think about, I'm using the same scheme that is shown up here. Think about the plane, and think about the cobalt is sitting right in the center, and then the one that pointing to you will be used is the wedges, and then the one that pointing away from you will be a dotted line. And then the one that is actually on the same plane is going to be just like a little line. So you have these 4 things that need to be positioned, and then this is almost like putting a little line with a line sticking up and lining sticking down, and this one has essentially 8-sided because each one is like a pyramid. If I can draw this, if you allow me to draw, right? If I draw the top, this is like a pyramid with 4 sides, and then this is the other one, right? And this is another 4 side. So it's an 8 side. That's why it's called octahedral. Right? So that's the name coming from, and I think that you should look for something more in the future if you want to know about a little bit more about the octahedral. So octahedral has this unique nature, and if you flip this structure is pretty much always the same. That the axial position and the dispositions, they are all equivalent to each other. Okay. But now we are seeing this compound called chrome sitting in the middle, the cobalt. Okay, so I'm going to change this one. This is from the slide, so now I'm going to change for your problem. So this is now instead of cobalt, this is a chrome, and the chlorine. So the chlorine can be situated here, and then the rest of them will be ends up doing this linked diamine. So that's the one. So it's like at the top of the pyramid, so I'm forming this complex with a basal plane. At the bottom of axial position of the nitrogen, and they will form this position, connected one. So this is each one is a diamine, and this is a chlorine, which is called a chloro, which is a negative ion, forming a complex, and overall you will be a positive ion. And so the other example that you can imagine is the chlorine. Now I'm just doing the shortcut way. So think about these are the planes. So this is a plane that is forming. Let's do it one more time. So this is more like a plane. Okay. And then there is something that's sticking up, something sticking down. Okay. So that is an octahedral idea. And then this time I am going to put the chlorine up. So let me use the same color. Chlorine up, down. Okay, so this is where the positions of chlorines are. This is a one is on essentially the one on the right. This is on opposite side, right? So that's a good to know. And this is one sort of what you call the same side, one neighboring side, right? So similar side, same side, right? And then you can finish up the rest of the drawing saying, okay, it must be a nitrogen connected this way, nitrogen connected that way, and this is how they form. So I can see that this is what you call the trans complex, and this is what we call the cis complex. Okay, so there are two possibilities putting these two chlorines on the same side and the opposite side. And then is there a non-chiral isomer of this compound? Right? And if you think about, this is one of the ways that to understand this is coming from your class slide. And one thing that you can understand is when you draw this, and this is a cis compound, and this is a mirrors. So this is a mirror images of chlorines on this side, now chlorine the other side, and everything is essentially mirror images. Once you make this is essentially the mirror images. This is mirror images if you bring it to here, and they are not superimposable. Means not superimposable. What that means in a plain English sense, it means different. They are different. Okay, different means it is an isomer. Okay, same connectivity but different spatial arrangement. So they are isomer pairs for the cis. So they are the one that they show as an example here. Right? So this is an example of, I think that if you have pay close attention to it, this one is a 1, 2, 3, right? So any metal complex with this tris diethylene amine, and that they can form this non-superimposable, the mirror images. They also can be possible. So what that means is this one, cis complex, they can form chiral isomers. Whereas a trans, if you put mirror images here, right? Put a mirror. You put down the mirrors. You find out you essentially mirror images is actually, this one is you find a superimposable. Okay, so therefore this one cannot form optical or chiral isomers. So is there any non-chiral isomers of this complex? Yes, it is for trans, and you can say trans CR Cl2 En2 plus complex, and then they form the non-chiral one, right? So this is an answer from the textbook. The answer key is generic answer key. Trans isomer is non-chiral, whereas the cis isomers they form chiral pairs. So these are what is called the chiral pair. Okay.